Aleksei Kondratenko je doktor znanosti i istraživač na Sveučilištu Politecnico di Milano s iskustvom u konstrukcijskom i seizmičkom inženjerstvu. Njegov glavni istraživački interes je poboljšanje održivosti industrije u arhitekturi, inženjerstvu te graditeljstvu primjenom inovativnih digitalnih tehnologija. Trenutno vodi razvoj softvera koji za zadatak ima olakšati inženjerima optimizaciju projektiranja zgrada u smislu pohranjenog ugljika.
All right, so I hope you can see my screen and that everything is all right. So, good afternoon, everyone. My name is Aleksei Kondratenko. I'm PhD student, PhD researcher at Politecnico University of Milan, Politecnico di Milano, and I would give you a lecture with the name of Carbon Capture and New Regulations. I'm working on projects mainly in civil and structural engineering related to, let's say, carbon dioxide emissions and their reductions in engineering industry. So I would love to share with you some experiences and tell you where we're going, actually, in this sense. But first of all, let's state the problem, greenhouse effect. I will just go very, very fast through this because I think you are familiar, or at least you heard about it. It's more or less everywhere, this greenhouse effect. Basically, what it means that our planet, Earth, receives sun radiation. Some of it reflects even without hitting the Earth. But when it hits, Earth emits this heat back to the space, let's say. The problem is not all the heat is emitted back. Some of it is trapped in the Earth by greenhouse gases. Basically, it means if we would not have any greenhouse gases, we would just be dead, right? It will be too cold to live on the planet. So we need something to trap some heat in our planet. However, the problem is recently we are trapping too much heat, which means it's going hotter and hotter every year. This graph shows it very well. So it goes from 1880, so the start of the first industrial revolution. And you can see year by year that especially in the last 30 years, it's increasing a lot. And now from this 1880, we have a 1 degree increase of its average temperature in the world. And you can, of course, imagine, like, you can say, oh, it's just 1 degree. Is it really a big deal? Like, why are we worried about it if it's just 1 degree? Like, I had 24 on summer, now I have 25, I'm okay with it. The problem is it's 1 degree averagely on the Earth, but this temperature, unfortunately, is not distributed equally all around the planet. So you can see, for instance, on these graphs, especially on the left, if you have 1.5 degree of, let's say, increase, that in some areas we will have the coldest nights and hottest days decrease of 6 to 8 degrees of Celsius. So I think if you go from 28 to 36, it's quite, you can feel it, right, as people, as humans. The problem is, as you can see on these two graphs, that's on the, let's say, where we have a lot of ice, we have a very big increase, which means ice is melting, of course. It's the big problem with the potential floods and etc. And also some areas, especially in Middle East, in the Southern Europe, I think also Croatia affected. It's like 4 or 5 degrees of increase in temperature, even though overall in the world it's just 1.5 or 2. So it basically means also for vegetation, for corals, for heat, you see that increase of just 0.5 degree of Celsius, it can give us 2, 3, 4 times, 10 times worse in terms of, let's say, everything we have, more floods, more heat, and etc. The problem is we are going towards this 1.5 and 2. We actually going to reach 1.5 like in 20 years, maybe even before, because the temperature is increasing now exponentially, which means it's increasing faster and faster every year. And of course, we are not like just watching it and trying to do nothing. A lot of politicians meeting and for so-called climate conferences. It was a Paris conference. Maybe you heard it was very, very influential 6 years ago in Paris. Last year it was a COP, so-called 26 in Glasgow, which means politics from all over the world try to do something with it, try to do regulations, try to speak with each other, try to say something like, oh, China, please stop emitting so much carbon. China says, oh, sorry, it's like you were emitting this carbon for the whole last century, why I need to stop now? And this battle is just continuing. So as you know now, like it's very naive to think that in a world where, as we recently noticed, the wars are still a case, that the whole countries will somehow have an agreement of doing something. So they are speaking, they're trying to regulate it because it's quite urgent nowadays, but don't believe much that these politicians will reach something very, very crucial, and the whole world will go towards something altogether. Unfortunately, it's not possible nowadays. So let's speak about greenhouse gases that are causing this temperature increase, so that possible heat waves and floods and other disastrous things. So we have three main greenhouse gases: nitrous oxide, carbon dioxide, and methane. And you see that they are quite different in terms of influence to us. Carbon dioxide is like taken as a norm, so it has like greenhouse potential as 1. Methane 25, nitrous oxide around 300. It basically means that if you have 1 kilogram of each of these gases, nitrous oxide is 300 times more dangerous and hitting our planet 300 times more than carbon dioxide. And for methane, it's 25 times more than carbon dioxide. So we have greenhouse gases, but they are affecting our planet in different ways. Let's speak about sources of these gases. So for nitrous oxide, it's mainly fertilizers and these lovely pigs, but not the pigs itself, but their manure. Manure, maybe if you don't know this word, the word shit would be much more familiar to you. And this is not a joke, actually, the manure, but let's be civil here, let's speak manure. So manure of pigs is actually very toxic, and it's no joke, and it has a lot of nitrous dioxide, and fertilizers at the same time that we use in our soil are also affecting our earth and our planet in a bad way. When we speak about methane, first of all, it's landfills. Of course, it's gasoline and let's say how we are doing things with oil and burning it, etc. And also cows. Another time we speak about agriculture. For cows, it's very easy. Cows have very particular stomach, which means they're eating a lot of carbon, which is, of course, in grass and etc. And their stomach somehow transmitting this carbon into the methane. So when they are, you see that we have two ways, from the mouth or from, let's say, another time manure. So when any time that's some gases go out of a cow, it's actually affecting our world in a bad way. And apart from the jokes, if you imagine that if cows were a nation, just imagine it was the whole country of cows, if you put all the cows in the world, that they would be the third country in terms of emissions after US and China. But the US and China emitting a lot of stuff, producing a lot of things. Cows are just living and producing gases, and that's enough because we have so much cows, actually. We have so much cows because the demand for meat and for milk products is very, very high nowadays. So it's actually a very, very big deal. And then, of course, carbon dioxide, the main topic of today's discussion. The main sources are electricity. You probably know that we are usually burning coal to get electricity, or gas. For oil, it's producing all the materials almost that we have. And of course, it's transportation. So let's speak which gas is leading the way. Carbon dioxide, even though it's the least harmful, as we have seen, we have so much of carbon dioxide that it is dominating all the gases. Let's say in this case, you see methane and nitrous oxide, they are normalized to so-called CO2 equivalent emissions. So every year we have around 50 billions of tons of CO2 equivalent emissions. It's a lot, but I would just like you to remember this, because if you hear somebody is doing something that is reducing carbon emissions, and they say that they reduce a ton, you can say a ton, it sounds a big amount, right? But if it's ton out of 50 billions of tons, it's not that big, right? So this is something you need to remember, that we have 50 billions of tons of CO2 equivalent emissions, and this number is quite increasing every year, unfortunately. The COVID year was quite an exception, but now it's increasing another time. And the last thing, about these gases, to finish my introduction, that's they actually last for a lot of time. For instance, carbon dioxide lasts for hundreds of years, which basically means if now, let's say, all these climate conferences, they all made finally sense, and we are like, let's say, as humans, we evolutionized in a way that we stop emitting any carbon dioxide, all right? So we deal with this climate problem. But the problem is the temperature will still continue to increase because of carbon dioxide that was emitted before in previous years and in the previous even hundreds of years. You see that methane and nitrous oxide, they actually going out forever in a quite, methane is just in 12 years. But for carbon dioxide, it is a big deal, which actually means that we don't need just to reduce our emissions. We also need to capture, to take this carbon from our planet, from our atmosphere, and the carbon that was emitted even before us by previous generation, etc. Okay, so let's speak about carbon. And one thing that we would speak today a lot is that there are two, let's say, possible ways of dealing with carbon dioxide. One is carbon source that I was speaking. Then when we have release of carbon dioxide much more than, let's say, it's capturing from the environment. So it's like cars, everything. They are carbon source, right? They are releasing carbon. But also there is another quite opposite thing. Is carbon sink. When we are taking or capturing carbon much more than we're releasing it. And the typical carbon sink is, for instance, tree, forest. You're probably very familiar that tree is taking carbon dioxide from our, let's say, air and releasing an oxygen. So tree is a carbon sink. Also, the soil is a carbon sink, especially when we are growing some crops on the soil. And these guys on the right top are quite carbon capturing machines. Maybe you heard about them. They are now getting more and more attention. The problem is this machine taking 1,000 tons a year. And remember I told you, we have 50 billions every year emitted. So this machine takes just 1,000. And so we have around 20 of these machines now in our world. So you can imagine if you really want to have the impact that we will feel, we need kind of to build, millions of this machine. Can you imagine the whole, Europe or Africa is full of these machines to capture the carbon. And only in this case, it will really have an impact. But another carbon capturing tool, or let's say another carbon sink, could be a building. And this is how we are transitioning towards today's topic. Today's topic is more, let's say, oriented towards engineers, civil engineers, architects, etc. So buildings can also be considered as carbon sink, the source that has, let's say, taken more carbon than emitting. Of course, nowadays it's not the case, but let's speak, what do we have? Engineers, and probably today we have a majority of engineers in the room. What do we have to do with all these carbon emissions? The problem, of course, that's apart from all CO2 equivalent emissions, 40% comes from buildings, 40%. So you can imagine if you really concentrate on reducing these emissions from building, we can have a big impact, right? Because it's almost a half. 28 comes from building operations, mainly electricity and stuff, and 11 from building materials and constructions. And this picture, I think, is very, very, for me, it was mind-opening, to be honest. We see just a house, and it's quite small. But what is behind the production of materials and etc. is a lot of factories, a lot of electricity, a lot of transportation, and a lot of emissions, unfortunately, for each building that we have. Types of carbon, by carbon, I will mean carbon emissions, carbon dioxide, okay? Just I say carbon to simplify it, but by carbon, I will mean carbon dioxide. So types of carbon dioxide that we have in our buildings are two embodied carbon and operational carbon. And operational carbon, probably you're very familiar. It's electricity, okay? Electricity, heating, everything that we are, let's say, need in the building to kind of sustain our life, to be in the heat, to have electricity, etc. And there is also embodied carbon. And embodied carbon is emissions from manufacturing, transportation, and installation of building materials. So actually, I believe building you are now probably made from concrete. So it was actually a lot of carbon dioxide emitted to manufacture this concrete, to deliver this concrete on site, to build the building, etc. And this is, I hope it's, in my computer it's GIF, so it's an animation. I hope in your case it's also an animation. I mean, I hope it works. So it basically shows the relationship between so-called embodied carbon and operational carbon. And you see if you build a building in 2020, it's only embodied carbon. So this is something that we need to take into account. When we build it, of course, we don't spend, the building itself does not spend any electricity because it's not finished. It's only embodied carbon. And then only after, when buildings start to function, when they start to spend electricity, heat, etc., then only operational carbon catching up. So if you're saying that we need to decrease these carbon emissions right now, we need to concentrate a lot on embodied carbon, because this is something that we have one just building is built. And then, let's say after 100 of years, we have kind of 60 to 40, so then operational carbon is bigger than embodied carbon. However, the problem nowadays, as you have seen from the previous GIF, embodied carbon is very, almost as important as operational carbon. So we need to consider them both, right? We cannot consider just operational. However, what we see, unfortunately nowadays, that's all the architects, architectural firms, norms and rules are mainly concentrated on operational carbon. And a lot of architects who are now, let's say, getting familiar with embodied carbon is quite actually a new topic. 2 years ago, almost no one was speaking about it. Now people start to speak about it much more. So a lot of architects, also Norman Foster, etc., they are, let's say, criticizing so-called BREEAM or LEED certificate. Probably you heard about LEED certificate if you're an architect. A lot of, let's say, constructor company like bragging that they have a LEED certificate, platinum, gold, whatever. But the point is to achieve this LEED certificate, you need to get so-called 80 points, and only 3 out of 80 is for embodied carbon. So can you imagine? Embodied carbon is quite half of all the emissions. But instead of, let's say, 40 or 30 points, the LEED certificate gives just 3, kind of ignoring embodied carbon at all. And this leads to the very ridiculous example of this Foster plus Partners building, Bloomberg building in UK, London. That's, of course, it's reached platinum LEED certificate. So biggest points. A lot of people are saying net zero carbon building, like look at us, we in UK are building like in a new level. The problem is, of course, it's operational carbon perfect, but they use a lot of bronze and aluminum parts to achieve it. So actually the embodied carbon was much bigger than if it would be initial design, let's say, if they would not try to reach operational carbon. So the point is the increase in embodied carbon overpassed the decrease in operational carbon in this building. So they tried to reach, let's say, very, very carbon efficient, net zero building, whatever, but seeking to satisfy this LEED certificate, they actually they emitted even more carbon dioxide than they would do if they just do a regular structure. So this is unfortunately the consequence of it. Fortunately, nowadays people are opening their eyes and understanding what is embodied carbon and that it also actually matters. And in this sense, the very important, the crucial concept is so-called building life cycle. Which means we have a building now, but how the building, what actually was before we enter this building and what will happen after with this. So of course, we need to build our buildings from some material. So we need to extract them, we need to transport to factory, manufacture them, transport them to the site, to the building site, construct the building, and it's all embodied carbon, right? Then we have use and maintain our building. So this is where operational carbon comes in, electricity, heat, etc. And then after our building is still kind of old, whatever, we need to demolish it. We need to do something with waste and landfill or recycle it. And as you see, it's all over embodied carbon. Only in operational, it's only in use of the building. Actually, use of the building at the stage that the building is now. For instance, building in which you are now, it's in use stage. But we need to understand that actually there are very big and important stages before the building is in use, and it's only embodied carbon there. However, this is linear building life cycle. But when we speak about circular economy, we need to transfer it toward the circle, which means after the use of building and its end of life, some of the materials of the buildings that we have now can be used for another building, for a new structure. That's how this circular stuff actually works. Of course, if you put all the, if we demolish our building and put all the material left to the landfill, then of course there is no circular thinking here. But if you recycle something, or better even reuse, then some parts from our current building can be used in the new structure. This is what we call building life cycle. And also, let's see how can we reduce this carbon. Okay, we understood the problem. We understood embodied carbon, operational carbon. Okay, sounds very depressing, right? We are kind of, if you are an engineer, an architect, you're going to work in the industry that is responsible, actually a lot for the planet disaster that is going to happen with us. So it sounds quite depressing. Maybe you would like to quit it and say, no, I don't want to do that. But the good thing that we can reduce both operational and embodied carbon. And for operational carbon, it's like something like passive house design in a way that the building needs to use as least electricity and heat as possible. Then, of course, the source of electricity could be renewable, so we don't need to burn coal or oil or whatever to get electricity. And so finally we can reach totally zero here for the, let's say, good design and also decarbonization of the whole electricity and heat grid. And of course, using like something like heat pumps instead of gas to heat our buildings. For embodied carbon, it's much harder. First of all, as I told, it's a lot about design, build less, transform and reuse. And build efficiently, minimize waste. But even if you do it all, we still have something. Because, I mean, we cannot, let's say, emit not carbon at all when we produce materials. Then we can offset some carbon, offset by means of, let's say, growing some trees, doing something with the soil, and etc. And when we speak about, okay, how can we reduce embodied carbon? I mentioned it already, but of course the best case is not to build at all, okay? But if you try to convince all your clients not to build at all, you probably have no job, right? So you are very, very climate friendly, but have no job because you convinced all your clients to not build buildings at all. Congratulations, very environmentally friendly, your company is bankrupt. So in this case, we better say that not build at all means not like convince your clients to discard the whole project, but to do so-called adaptive reuse. So reuse or retrofit the existing structure instead of building the new one. So in this case, you would not need to actually manufacture any materials. Then material reuse, as I already mentioned, and also use of environmentally so-called friendly materials such as timber, bamboo, and etc. So then concluding my lecture and speaking actually about some regulations that are coming. This is another time building life cycle that I have already showed to you, but now it's more in terms of, let's say, norms and rules. So as I already mentioned, this production, construction, use, and end of life stages are decomposed by some, let's say, letters and norms. And for a production stage, we have first of all, so-called to quantify all this embodied carbon. So you can say, okay, it's very, very, very good. We need to reduce embodied carbon. Nice news. But how can I actually understand how much embodied carbon is in my building? How can I calculate it? Is it possible to calculate? It is. It is the very easy formula is like quantity of the material, whatever it could be, cubic meters of concrete or tons of steel, multiplied by so-called carbon factor. And carbon factor is actually how many kilograms of CO2 emissions were emitted for kilogram of your product. And you can see that these coefficients are given in norms, in databases, so-called. And what is funny to see that, for instance, for concrete, it's much smaller than for steel, and then even for timber, which probably can give you the information that concrete is the most environmentally friendly material. But of course, it's misleading because in terms of quantity, we need much more quantity of concrete than steel and also timber to build our building. And quantity is, I think, more or less clear for everyone. You just calculate the volume of a structure. But this carbon factor is misleading because you can say, okay, this value, very good, but how do you achieve it? Why is for concrete 0.1? And who give you this value? Why it's like this? It actually goes from the so-called databases that are particular for each country. Not each country have it, though. So, for instance, in UK they have it, in Germany, Italy, mainly in Europe they have it a lot, in US. In Croatia, I doubt it, but maybe you also have your own database. But with what is much more, let's say, reliable way to understand this carbon factor is just to use APD, Environmental Product Declaration, which is something that if you use particular concrete from particular producer, this producer gives you the particular value of this carbon factor because this producer knows how exactly he or she produces the concrete, right? So this also means that if you are architect or engineer and you design your building, you better ask for this APD for the manufacturer, because these carbon factors I show from databases is kind of average from all. So it could be, value could be any actually, because it depends on the particular producer. So nowadays, almost all the big producers in the world have the EPDs, and if you're a producer of concrete or steel and you don't have this EPD, you of course have competitive disadvantage. The impact of the design, you see all these stages like from A to D. As I mentioned, like building, reusing, waste, and then like end of life. You can see that we can either design for reuse. In this case, the D is very big, so we can kind of offset. Design for reuse means that when I design in my building, I think that someone will probably dismantle it and use some materials in the future structures. And then, of course, we can build new buildings with the reused materials. In this case, you see that the impact of the production stage is very, very small because we don't produce much materials because we reuse it from previous buildings, or we use, let's say, or we do a retrofitting of existing structures, so we reduce manufacturing emissions as much as possible. Then when we calculate this embodied carbon, we normalize the results by meter squared, because I mean, you can have 6-story building or 10-story building. Definitely 10-story building emits more carbon, right? But if you try to compare them in terms of how carbon efficient they are, you need to normalize it by square meter of the ground. And these like values nowadays are quite necessary to calculate. In these countries, as you see, Denmark, Finland, Norway, Sweden, UK, France, Germany, Holland, in all these countries, if you want to achieve building permit, you need to calculate embodied carbon. It's not like something, oh, it's better to do. You have no choice. You have to do it if you want your building to be built. In Holland, they even went further, and in France from this year, from next year as well, they went even further. They don't ask everyone to calculate embodied carbon. They even put some norms, which means these values per meter squared are limited. So if you want to build a structure, they need to be below particular threshold. And if that, so for instance, of course, when you design any building, you need to be like aware that it's safe, so it passed all the checks from the code. But nowadays, in countries like Netherlands and France, you also need to like this building to emit as less embodied carbon as possible. And these norms are given for each structure, for each, let's say, type of building, office or like office, hospital, university, and etc., residential. So, and this is something that is going to happen actually all over the world. It's just starting, as it's usually starting from Northern Europe, but I think it will also come to Italy, to Croatia, etc. So this calculation, this consideration of embodied carbon in your design is quite crucial, and in some countries is already necessary, but you better start learning it now, because in the future it will probably be necessary in your country as well. And the last thing, like something that is proposed by some British guys, and probably you saw this kind of picture in on your fridge, I don't know, on maybe kind of electronics you have, vacuum cleaner, microwave oven. I don't know, at least in Italy, I can see it almost on all electricity parts, on all electronics. I believe in Croatia, you probably have something similar, which means like, let's say, the characterization of your, how environmentally friendly is your fridge or whatever. So there is a proposal to do something similar for buildings as well. So it is a proposal. It's not like something approved, but very, very probably our future buildings will have something similar on them. So I think that's it. That's it. Bibliographies like list. If you will need, I think you have a PDF. So thank you very much. And I don't know what is the format. Maybe if you have questions, or like maybe Domagoy or Hanna will tell me what is the format then. But thank you for your attention.